So next, what you guys are going to start doing is looking a little bit at what happens when you've got ramps and stuff like that. And of course, a really common thing is, you've got somebody on a ramp. You're on a skateboard. That's a terrible skateboard. Something like this, and they roll down the ramp. And when, of course, ask what's pulling the person down the ramp? Well, of course, gravity is pulling them down. But here's the thing: gravity doesn't go down. Gravity goes this way. So then, what's pulling them this way? I mean, because you go down the ramp because gravity's pulling you down, but gravity pulls down, not just down ramps and stuff like that. So what we're going to start looking at is what happens on inclines and how gravity pulls things down ramps, even though it's actually gravity going straight down. So we're going to start looking at this and some of the other things that kick into the scenario and the forces required for things to go down ramps. Okay, so it's called inclined planes, inclined forces, that type of stuff, which are used for lots of different things. Okay, so to help us out, we're going to use a sheet here to help us out to sort of look at some things that are actually going on. So you got a basic box on a table, really, really simple, very, very standard, really typical. Of course, you've got the force of gravity pulling down. You'd have the normal force going up. Really, really simple. And of course, those two forces would be equal to each other. One creates the other. Really, really, really simple. Okay. Now, of course, the trick for this is not Newton's third law, because these forces are they're both acting on the same mass. And some people, they'll look at stuff like this, that Fg and Fn, those are Newton's laws type thing, like Newton's third law were equal and opposite forces. Well, they're equal forces, they're opposite, but since they're acting on the same mass, they're not Newton's third law paired forces. But anyway, so those are the two main forces acting in the box. This is what you guys have worked with for a while already. So now what happens when we take a box and we put it on a ramp? Well, the force of gravity is still going down. That hasn't changed. And this over here, this is still the normal force. Now, it's still the normal force because by definition, if you guys remember, normal force or natural force has to be perpendicular to the surface. I mean, that's the definition of it. But you can see they're no longer opposite anymore. So it's just a perfect little illustration that Fn and Fg aren't always the same and not always equal and opposite. So over here, we still have Fn, we have Fg going straight down, but they're not equal and opposite anymore. But that doesn't mean one doesn't have anything to do with the other. Why is there normal force in the box? Well, because the box is pushing down into the ramp and the ramp pushes back up on it. But it's being pushed down on the ramp because of gravity. So gravity is definitely part of the normal force. But gravity isn't just pulling the box down to the ramp to create pressure. It's also pulling the box down the ramp. So it's causing motion. So gravity is actually doing two things at the same time, which is a little bit different. Now, the other part that kicks in, if you look at the coordinate system, you can see that the coordinate system, my XY plane, has actually been rotated. And what you want to do is you want to rotate your reference frame or your coordinate system. That's because when the box is sliding down the ramp, if you don't rotate your system, if we would go back to this system and the box was sliding this way, it's moving in two dimensions at the same time. You're moving, there'd be X motion and Y motion, which gets complicated. But if we rotate the system, so the box is moving like this, it's only moving in the X direction, which makes things an awful lot easier. But the consequence of this is, if you look at the force of gravity, which is going straight down on the picture, it's no longer straight down on my coordinate system, or force of gravity is going this way. It's actually, according to my reference frame, at an angle. So since the force of gravity is at an angle, according to my new reference frame, it can be broken apart to do different things. All right, so the force of gravity actually does two things. So the force of gravity does a couple things. First of all, it causes the Fn to exist, but it also causes the motion down the ramp. And what we've done is we actually rotate or turn our reference frame. And because of this, the FG is now at an angle, which means we can actually break apart the force of gravity. Okay, so we can actually break this thing apart. All right, so let's go to the third picture and sort of see how that kicks in. So if we go to the third picture here, my force of gravity is going to be broken apart. My Fn, if I go back up here, my Fn is actually along the vertical axis, along the y-axis. They're perfectly parallel. And my force of gravity is at an angle. So if I break apart my force of gravity is doing two things. It's going down this way, and it's also going across this way, and then hopefully you can see sort of how it can do two things at the same time and how things connect. This right here, this is my FG in the y direction. This is my FG in the x direction. They do different things. Now you can probably tell already, here's my Fn again, that my force gravity in the y direction is directly connected to this. They're equal, they're opposite. So what's occurring, my FGY, this is what actually creates the normal force. And the flatter the ramp, the bigger FGY is going to be. So FGY creates the normal force. So then what about the FGX? Well, you can see the FGX is actually pointing down the ramp. So that's the part that actually causes the box to accelerate. So the FGX part, this is what actually causes the motion. And how much you get at FGX or how much FGY you get totally depends on the angle. So the angle is a big part of this. And you guys know this. I mean, if you got a ramp with a really, really, really small angle, it barely moves. But something like a really steep ramp would. Now, if we look at the angle, of course, the ramp has an angle right there. And if you can visualize the geometry and that type of stuff, you can see that it is the exact same angle that is right there. So those two angles are equal to each other. And as this one would get bigger, so would this one. This one would also get bigger. So if we look at how to calculate the FGX and the FGY, it's actually pretty simple. FGX, if we want to calculate FGX, we're just going to take the force of gravity and then use trig to solve for it. Now this is going to be a little bit careful because we're not using this angle in the ramp, we're using the angle in the actual FG triangle. And if I look where FGX is actually opposite to the angle. And if you're solving for the opposite, you got to use the sine function. So that would be the force of gravity times sine theta. Where for FGY, that is adjacent to the triangle. Okay, it's right here. It's adjacent to the angle. And that means that it would be the FG times cos theta. And it's common for us to have used cos to find x's and sines to find y. That is stuff we've done, but this is where it gets flipped. Because if you look at the triangle, the force of gravity triangle is actually rotated 90 degrees compared to the ramp triangle. So since it's been rotated 90 degrees, the trig functions actually get flipped around. So you will commonly see FGX as mg sine theta, and then this would be mg cos theta, and that's how you can solve for how much force is pulling a box down and how much force is being used to create normal force between the surfaces. Now, even if, the trig function type thing, if that angle's really, 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 really small, it would barely go down. The FGX would be really, really small. So it makes sense for the angles, because if I look at this, if sine theta is really, really, really using like a really small angle, sine theta of a really small angle is really, really, really small. So FGX is really small. That makes sense. If I use cos there by mistake, the cos of a small angle is really big. So how could a really small angle cause a whole lot of FGX? That doesn't make any sense. And that's because for this, the trig functions are flipped around. So FGX was going to use sine theta, and FGY is going to use cos theta. Okay, so let's just do a little bit of work here and sort of show you how this type of thing actually works. Okay, so I'm actually going to go back to my little skateboarder guy that I had before, And let's say we've got, let's do something really simple. So we level a 75 kilogram skateboarder, and let's say he is on a 20-degree ramp. Let's do something really simple. What is the acceleration of my skateboarder? Well, the force on him, I've got FGX is pulling him down. I don't actually need to worry about FGY right now. All I really care about is my FGX. So my FGX would be mg sine theta. If I punch that out, that gives me about 252 newtons. So there's 252 newtons pulling him down the ramp. Okay, pretty straightforward. So then to find his acceleration, that would be F over m. Now this is the only force acting on him. I'm just going to use the 252. That's it, no big deal. So I divide that by the 75, and he's accelerating down the ramp at about 3.3 meters per second squared. That's it. Okay, so it's very similar to the stuff you guys have done before, except FGX, FGY, the idea of breaking apart the force of gravity to do different things. Okay, so let's try something else. All right, ooh, nice purple triangle. Change that. Okay, so do something really simple. All right, so let's see, gotta put an apple on here. Okay, all right, apple. Okay, let's say this is a 25-degree angle. Let's say, actually kind of looks like a tomato more than an apple, but whatever. Let's say we've got a 65 kilogram tomato, and let's just start simple. What are FGX? What are FGY? And then we'll piece some things together. So let's just start with my FGX. So my FGX would mg sine theta. So I'll do this 65 times 9.81, and I'll times that by the sine of 25 degrees. And I've got an FGX of, I'll just round off, around 270 newtons. So there's 270 newtons trying to pull the tomato down the ramp. Okay, so now I'm going to find my FGY. Now my FGY would be mg cos theta. So very similar, 65 times 9.81 times the cosine of 25 degrees, which gives me about 578 newtons for FGY. Now this is also going to be my normal force, because that's what FGY does, is create normal force. So then what if I had a coefficient of friction? Then normal force would then give me my friction. So let's say the coefficient of friction between the giant tomato and the surface over here, let's say the coefficient of friction was, let's just go with 0.30. Well, now I can find my friction. My force of friction is just mu Fn. Well, I've got my mu, my Fn is just my FGY, so if I multiply those two together, I will get how much friction there is. And if I do that, there's 173 newtons of friction. And now to figure out the rest, I mean, this is the same type of thing as before. How much is trying to move my tomato? Well, there's 270 trying to pull it down the ramp. Well, how much is trying to slow it? Well, apparently 173 newtons of friction is trying to slow it. So if I just take those two and subtract them, I can get my net force. My net force would just be the difference between the 270 and the 173. So that leaves me a net force of 97 newtons. And once I've got that, I could find the acceleration as just net force divided by mass. So take that 97, I divide that by the 65, and I get about 1.5 meters per second squared. And that's it. So this is very, 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 very similar to the other stuff that you guys have done. You know, it's a lot about what's trying to move it, what's trying to hold it back, put the forces together, get the net force, get the acceleration. Most of the calculations are the same. The FGX and the FGY are the only two newish type things. the rest is very similar. Friction is the same, net force, summation of the forces, acceleration the same. A lot of it's the same. Just a different perspective on it. So you get the FGX and the FGY, and probably the biggest difference is often in the other stuff you guys did, mg was equal to Fn. Here they're not equal. It's only the y component of Fg is equal to Fn. But then the rest of it's actually very similar. Okay, so, and again, just like other dynamics, the more you do, the more comfortable you become at doing this type of stuff, and it typically works out pretty well based on the stuff that you guys, or building on the stuff that you guys have done previously.